Welcome to the deep dive. Today, we're digging into something really central to making AI smarter. How do we get large language models, LLMs, to handle complex tasks well, especially when it comes to reasoning over tables?
Right. Those spreadsheets, those databases,
Yeah,
they're everywhere. Business reports, scientific data.
exactly. And it's kind of surprising, but LLMs often get tripped up. They make mistakes that seem simple to us, or they just get lost in all that structured information.
Yeah, they can struggle with the nuances.
So our mission today is to unpack this fascinating new framework called MAPA. That's MAPLE, stands for Multi-Agent Adaptive Planning with Long-Term Memory.
hmm
And the idea behind MAPLE is basically to give LLMs a bit more human-like ability to solve problems, learning from mistakes, remembering what worked before,
Yeah?
that kind of thing.
Yeah, and it really gets at a core limitation of how most LMs work now. They typically use what's called single-pass inference,
Single pass, meaning,
meaning they try to get the answer in one shot,
hmm,
like throwing a dart blindfolded, hoping you hit the bullseye first time.
okay. So no checking, no second chances.
Pretty much. There's no real error detection built in, and maybe more importantly, all the experience from trying to solve that problem.
Yeah.
It just gets thrown away.
Which is totally different from how we work, right? We try something, we check it, we think, okay, that didn't work, why not? And we adjust.
Exactly. We reflect, we learn. Maple's trying to build that reflection and learning capability into the AI.
Okay, so let's unpack this table problem more. Tables are everywhere, like you said. Why are they so tough for LLMs? Is it just finding the right cell, or is it deeper?
Oh, it's much deeper than just finding a cell. Answering questions over tables is incredibly challenging because it often needs, multi-step reasoning.
Right.
You have to recognize relationships between cells that aren't explicitly stated. Like this column relates to that column in this specific way.
Implicit connections.
Exactly. And it needs really precise interpretation of the context. It's not just finding USA in the table, it's understanding what USA means in that row, in that column, relative to everything else around it, understanding the whole structure.
Makes sense. So what about the existing ways LLMs try to handle this? You mentioned single pass. What else is out there, and why isn't it quite enough?
Well, yeah, the single forward pass methods, like we said, have no error checking.
Hmm.
So if the LLM makes a mistake early on,
It just snowballs.
it just snowballs, the error propagates right to the final answer. Then you've got things like React-based approaches. They're a bit better. They get some feedback from the environment, like seeing the results of an action.
Okay.
But they still don't really have a systematic way to verify their own reasoning or self-correct properly. It's like seeing your dart missed, but not really analyzing why or having a clear plan to adjust your throw.
Gotcha.
And even some multi-agent approaches, they often just focus on tweaking the final output. They don't necessarily fix the underlying reasoning process that led to the potential error.
So polishing the answer, not fixing the thinking.
Kind of, yeah.
Yeah.
But the really critical missing piece, I think, across almost all current systems, is that they just discard the problem-solving experience afterwards.
They don't learn from task to task.
Right. There's no accumulation of knowledge, no building of strategies over time based on past successes or failures. And that's probably the biggest difference compared to how humans get better at complex tasks.
Okay, so this is where Maple comes in, trying to mimic that human process. The paper talks about a feedback-driven loop using cognitive agents. Sounds intriguing. How does that actually work, like different parts of a brain?
That's a good analogy, actually. Maple breaks down the whole problem-solving process into distinct stages. There's reasoning, then verification, then reflection, and finally, memory evolution.
Okay.
And each of these stages is handled by its own dedicated agent. Think of them as specialists. You've got the solver, who does the iterative reasoning,
Trying to find the answer.
right? Then the checker, who acts like a quality control inspector, assessing the solver's work.
Checking the checker, essentially. Well, checking the solver.
Checking the solver, exactly. Then if something's wrong, the reflector steps in, it diagnoses the error and figures out how to improve.
The self-correction part.
Precisely. And finally, the archiver manages the long-term memory, storing and organizing these experiences so the system learns over time. It creates this dynamic cycle.
And that dynamic adaptation seems key, right? It can adapt within a single tricky problem, trying again if it messes up.
Yes, it can.
But also across problems. So if it sees a similar question later, it can draw on past experience. It's not just about getting an answer, it's about getting better at finding answers.
That's the core innovation, really. It's designed to mirror that human learning curve.
Let's meet these agents then. Tell us a bit more about each one's specific job. What makes the solver tick, for instance?
Okay, so the solver. It uses something called the REACT paradigm, which means it interacts with the table, maybe it queries it, filters it, then it looks at the results, assesses the situation,
Reassesses the environment.
right? Reassesses, and then decides the next step, or decides if it's actually found the final answer. But what's really cool is that it uses two kinds of memory.
Oh,
Yeah, a working memory, which holds sort of immediate tips and corrections from the reflector for the current problem.
like short-term notes?
Kind of.
Oh.
And then a long-term memory managed by the archiver, which brings in historical knowledge, similar questions faced before, strategies that worked, common mistakes to avoid. This dual memory really boosts its reasoning.
Okay, interesting. So after the solver proposes an answer, the checker steps in. What's its checklist look like?
The checker is MAPLE's critical quality control. It looks at the solver's answer based on three main things. First, answer type checking.
Does the answer format match the question? Like number for how many?
Exactly. If you ask which country, the answer shouldn't be a date, right?
Yeah.
Second, format validation. Does the answer follow any specific formatting rules needed? Maybe it needs to be just a single number, not the whole calculation. And third, and this is crucial, evidence grounding. Is the answer actually supported by the data in the table?
Can you trace it back?
Precisely. If the question is, who won the most gold medals? And the table shows USA won 10, China 8, Japan 7. An answer like Germany clearly isn't grounded in the evidence.
Makes sense.
And the checker doesn't just say yes or no. It gives a score for each criterion, along with comments explaining why. This structured feedback is super helpful for figuring out exactly what went wrong.
Okay, so if the checker finds a problem, it passes the baton to the reflector. What does it do? Just point out the error?
It does much more than just point it out. The reflector is where the system gets its metacognition, its ability to think about its own thinking.
The self-awareness bit.
Sort of, yeah. If the checker flags an error, the reflector looks at the entire reasoning process. The solver took every step.
It diagnoses the root cause. Was it a misinterpretation? A faulty calculation step?
And then it generates a concrete, actionable improvement plan. Like, next time, pay attention to the date column, or recalculate the sum using this specific filter. It gives step-by-step corrections for the solver's next try.
So it actively prevents the solver from just making the same mistake again blindly.
Exactly. It enforces learning from the error.
And the final piece is the archiver. This sounds like the librarian of the group, managing that long-term memory.
That's a good way to put it. The archiver is what enables the system to learn from experience over the long haul. It does a few key things. First, memory summarization.
Condensing the experience.
Right. It takes everything about a problem-solving attempt. The table, the question, the answers, right and wrong, the solver's steps, the reflector's feedback, and distills it into a compact, structured memory node.
Like a case file.
Pretty much. Capturing keywords, tags, the operations needed, error types, what worked, what didn't. Then it handles memory retrieval. It can pull up relevant past notes to help the solver when it faces a new, similar question.
Giving it hints based on past experience.
Exactly. Or even help itself organize the memory better. And that leads to its most sophisticated function, memory evolution.
Evolution. How does memory evolve?
Well, it actively manages the memory base. When a new note comes in, it decides, should this strengthen connections to existing similar memories? Should it update metadata? It's about improving how knowledge is organized and retrieved over time. It even filters out redundant or less useful memories to stop the system getting overwhelmed.
Wow, okay. So it's not just storing memories, it's actively curating and refining its knowledge base.
That's the idea. It's quite advanced.
This all sounds incredibly sophisticated.
Yeah.
To help us, and you, the listener, really grasp it, can we walk through an example? The paper used one like, who was the top goal scorer previous to Landon Donovan? How would Maypeel tackle that?
Yeah, that's a great example of where simple logic can fail. So, round one. The solver might look at the table, see Donovan, see who has the next highest goal count, and answer, say, Clint Dempsey.
Okay, seems logical on the surface.
Right, but it misses the nuance. So round two. The checker gets this answer. It flags an evidence-grounding error. Its comment would point out that previous to likely refers to the time period or career span, not just the next highest scorer overall. It might even suggest consider players active before Donovan, like Eric Winalda.
Ah, so it's guiding the interpretation.
Exactly. So round three, the reflector takes this feedback. It analyzes the solver's steps and confirms the diagnosis. The solver misinterpreted previous to, ignored the temporal aspect. Its improvement plan for the solver would be specific. Reread the question. Filter players whose careers ended before, say, 2000, or who were active just as Donovan started, then find the top score within that group.
Much clearer instructions.
Definitely. So round 4 and 5, a solver tries again, following the reflector's plan. It filters the players correctly based on career timelines relative to Donovan's start and identifies the top scorer from that pool.
And hopefully it gets...
Eric Wynalda. So round 6. The checker now gets Eric Wynalda. It verifies. Correct answer, type name, correct format, single name, and, crucially, now grounded in the evidence when considering the temporal aspect. Check, check, check.
Success. And then the archiver steps in.
Yep. Round 7 and 8. The archiver takes this whole successful episode, the question, the initial mistake, the correction, the final answer, the steps involved, like filtering by date, comparing scores, finding the max, and summarizes it into a new memory note.
So next time it sees previous to or a similar temporal query,
It has this experience to draw on. In this particular case study, the archiver decided this note was distinct enough and didn't need to immediately merge it or drastically change existing connections, so no major evolution right then, but the learning is captured.
that really illustrates the iterative corrective process. So, okay, it works in this example, but how does it stack up overall? The paper tested it on standard benchmarks, right?
Yeah.
WikiTQ and TabFact using models like LumA3.
Yes, exactly. They ran rigorous experiments, and the results, honestly, they were pretty compelling.
How compelling.
MAPLE consistently and significantly outperformed the existing methods they compared against. On WikiQ, the improvement was up to plus 8.26% over the best baseline. On TabFact, it was up to plus 7.41%.
Wow, those are substantial gains in accuracy.
They really are. And importantly, this wasn't just with one specific LLM backbone. The advantage held up across different models, which strongly suggests the MAPLE framework itself is providing a fundamental boost to reasoning ability. It's not just a fluke of one model.
And didn't they do an ablation study too, where they take away parts to see what each one contributes? What did that show? Because it helps understand, why it's better.
Yes, the ablation study. It's super insightful. They started with the baseline method, which scored around 45.58% accuracy.
Okay.
Then just adding the solver agent with its multi-step reasoning, but no other MAPL components. That alone jumped the accuracy by a massive 18.2 points, up to 63.81%.
Huge difference already, just reasoning iteratively.
Huge. Just how limited single pass really is. Then they added the checker on top. That gave another boost of 2.1 points, hitting 65.91%. Verification clearly helps.
Yeah, refinement.
But then, adding the reflector, the error correction piece, that added another, even bigger chunk, plus 5.2 points, bringing the accuracy to 71.09%.
So that thinking about thinking part is really powerful.
Incredibly powerful. And finally, adding the archiver, the long-term memory, that brought it to the peak performance they reported, 74.01%.
Wow. So each piece adds value and it really stacks up.
Exactly. It demonstrates beautifully how these different cognitive functions, reasoning, checking, reflecting, remembering, all work together and contribute cumulatively. It's not just one magic bullet, it's the whole integrated system.
That's fascinating. So beyond just the performance numbers, what did this deep dive, especially looking at the errors MAPL still made, tell us about the hardest parts of table reasoning for even advanced AI?
That's a great question. The error analysis they did, looking at the mistakes that remained after MAPL's multi-round process, was very revealing.
What stood out?
On WikiTQ, nearly 80% of the leftover errors fell into just two main buckets. Logical reasoning errors, like misunderstanding complex relationships or implications, that was about 40.4%.
Okay.
And counting and aggregation errors, like miscounting items or summing numbers incorrectly, especially in large tables, that was around 38.7%.
So complex logic and precise math, basically.
Pretty much.
Yeah.
What's interesting is that simple computational errors, like basic arithmetic mistakes, were really low, only about 4.1%.
Meaning MAPL's checking and reflection process is good at catching the simpler stuff.
Exactly. It effectively weeds out those basic slip-ups. So the insight for future work is clear. We need to focus on improving the core logical reasoning abilities of LLMs themselves and probably integrate more specialized, robust tools for handling complex counting and aggregation tasks accurately.
Don't rely on the LM for heavy math. Maybe use a calculator tool.
Something like that, yeah. Augmented strengths.
And what about the memory system itself? You mentioned evolution and filtering. Did they find an optimal way to manage that knowledge? You hinted at a Goldilocks idea.
They did. They looked at how different settings for managing the memory affected performance. For memory evolution, deciding when to merge or link memories, they found a sweet spot.
Not too much, not too little.
Exactly, the Goldilocks principle. If the similarity threshold for linking memories was too low, linking almost everything, the system got overloaded with redundant info. If it was too high, only linking very, very similar things, it didn't build enough connections. The peak performance for organizing the memory was at moderate similarity thresholds, around zero point 0.7 on both datasets.
Okay. Balance is key for organization.
Right, but interestingly, for actually using the memory to solve new problems accurately, slightly stricter criteria worked better. Lower similarity thresholds, around 0.3 to 0.5, were optimal for retrieving the most relevant past solutions.
Huh. So you organize knowledge broadly, but retrieve solutions narrowly.
It suggests different optimal zones, yeah. One for building a coherent knowledge base, another for finding specific answers. And the researchers noted this aligns really well with cognitive science theories about approximate learning.
How so?
The idea that we learn best when new information is neither too familiar nor too alien compared to what we already know. It has to be related enough to connect, but different enough to teach us something new. May-PLE's memory findings seem to mirror that.
That's a really cool parallel to human learning. Okay, so May-PLE is clearly a big step forward, but no system is perfect. The paper was pretty upfront about limitations, right? What are the main challenges or downsides for you, the listener, to be aware of?
Yeah, they were transparent, which is good science. A major one is computational intensity.
Makes sense. All those agents, multiple rounds.
Exactly. It involves multiple calls to the underlying LLM for each reasoning attempt, plus the overhead of the agents themselves. So it's definitely more resource intensive than a simple single-pass method. That could be a barrier for real-time applications or systems with limited computing power.
Okay, so speed and cost could be factors. What else?
Long-term scalability of memory. While the archiver's evolution and filtering help now, how well will it scale when the memory base becomes truly massive, containing potentially millions of experiences?
Keeping it organized and useful could get tough.
It could. Preventing knowledge dilution or retrieving relevant memories efficiently from a vast store is a big challenge. They suggest future work might need things like forgetting mechanisms, ways to prune less useful memories, or maybe more hierarchical ways to organize knowledge.
Like chapters in a library, not just one big pile of notes.
Something like that.
Hmm.
And the third main limitation they highlighted is the lack of external knowledge.
Meaning it only knows what's in the table.
Pretty much. May-PLE, as described, is focused entirely on reasoning based only on the data provided in the table. It doesn't pull in outside facts or common sense knowledge from the wider world.
So if a question requires knowing something not explicitly listed.
It would likely fail. Integrating external knowledge sources is a clear next step to make it more broadly applicable.
Right. So computational cost, memory scaling, and incorporating outside knowledge, those seem like the big hurdles to overcome next.
Definitely key areas for future research, building on what May-PLE has achieved.
Well, we've certainly taken a deep dive today into May-PLE. It's a fascinating look at how we can structure AI systems to think, check their work, reflect on mistakes, and actually learn from experience, much like humans do, especially when dealing with complex tabular data.
It really pushes the boundaries.
Yeah.
And it leads you to wonder, doesn't it? If breaking down reasoning into these specialized agent roles, solver, checker, reflector, archiver, with adaptive planning and memory is so effective for table reasoning, what other complex human abilities could we potentially model this way? What other cognitive processes could be modularized and replicated to make LLMs even more capable and, well, more intelligent across different domains?